Okay, so in this video we'll be designing a hexadecimal decoder or a hexadecimal driver. You can call it either one. And so we begin by looking at the part that is available to us to use on the simulation software. So typically they're called a 7-segment display, and that's because it has 7 different sections we see here in this schematic. There's 7 different portions or sections of the display that can be turned on or off, and typically these are of the common anode type. So what that means is you're going to have a VCC like this, and for the rest of the legs down here you're going to have the different sections of the display. So A, B, C, D, E, F, and G. Now in real life these components look a little bit different. It's sort of like a box, and kind of like this here. And they have legs on either side. And then here is the the display. That's what they look like, and it's not necessarily in order when you look at it here. Like, it's not that it doesn't typically go A, B, C, D here. You'll have to look at a schematic or a data sheet rather to see what pins are which. But for our purposes, we're more focused on the design aspect of this. So let's talk about common anode. So what that means is we'll have so if you look at the A section, for instance, the VCC is going to come in like this, and then it's going to go into the other sections. But let's focus on the A here. So in fact I can sort of draw a straight line here, and then dots, meaning that it goes to other diodes as well. And let's say that this is the A, and let's say that VCC is 5 volts. So, well, actually A is going to be this here, because this is the pin A. So let's say that A is equal to 5 volts, meaning logical 1, right? So I'm basically putting logical 1 into A. So that means that we'll have 5 volts here. And so the difference between here and here, it's going to be 5 minus 5, which is obviously 0. So there's a 0 voltage difference between these two. So that means that there's no current flowing through. So the LED won't be turned on. Now let's say that the logical value into A is 0. We're going to have a voltage difference of 5 minus 0 across the diode. So that's simply 5 volts. So what that means is we're going to have a current flow like that, and that is going to turn on the LED. So this is what we need to take into account when we make our design for the 7-segment display. Okay, so we want to count in hexadecimal, so that means we're going from 0 all the way to F, or to 15. And one thing about this is that I want each value here to have a unique representation. Therefore, let's look at 6 for instance. I have chosen this representation for 6, and for B, on the other hand, I have chosen lowercase b here. I can't make it uppercase because it would look like an 8, and if I make it lowercase it looks like a 6. So I have to make a clear distinction between B, lowercase, and then the number 6 here, and I have. Same with the letter D. I have chosen this lowercase setup. If I made it uppercase, it would just look like 0. So we know that D here, like this, is this is, we know that when we see this, it's a D. And then the rest of the numbers, have no problem. It's straightforward. So this is what we're going to be using for making our truth table. Okay, and here we are. I have my truth table. It's not completely filled yet, but since we're counting in hexadecimal, right, you have to use 4 bits. And so I have chosen to label them as W, X, Y, and Z, where Z is the least significant bit and W is the most significant bit. So we want to start with A. So basically A is going to be, if you look here on the right, we're looking at this section here. And as we go down this list from 0, all the way to F, we want to be looking at this section of each of the displays that we have here, of each of the representations rather. So, just to make this clear, basically we're looking at this as we go down the list, and so on and so forth. So let's go ahead and fill it out. So we're going to have 0, 1, 0, 0, 1, 0, 0, 0. I'm here, so 2 more zeros. And then we're going to have a 1 on B. So B is right here. A 1 on B. And it seems like I'm missing a 0, so let's put it there. We're going to have a 0C. We're going to have a 1 on D, right? And then 0, 0. So 1 here and 0, 0. Okay, so now let's do B. Get rid of these circles. So now I want to be looking at this section here for each of the numbers. So let's go ahead and circle them here, sort of make it obvious for ourselves what it is that we're dealing with. And so the reason I'm drawing the circle this high is because I want to be able to easily erase it. I have to make sure that I'm not looking at the neighboring LED. Otherwise, it could be wrong. So I have to make sure I'm circling the correct one. I did put these numbers pretty close together, but if I'm careful, I should be fine. So we have zeros all the way from 0 all the way to 4. So let's write that out. So 1, 2, 4. And then we have a 1 on 5, a 1 on 6, and then 4 zeros up to A. So 1, 2, 3. So that's up to A right here. And then we have B and C is a 1. So 1, 1. And then D and E and F. So D is 0, E is 1, and F is 1. So it's going to be 0, 1, 1. So you basically repeat this process until you fill the whole table. So this is not a state table like from before. This is simply a truth table. And we're going to be making some kernel maps once I fill out the whole table. Okay, so here we are. We're going to be now making the kernel map. You see here that I have a kernel map ready, and we're going to be making the kernel map for letter A. So we're going to have 7 different kernel maps, and we're starting with this one here. So we're going to be looking at these specific bits right here, this column. So I'm just circling it to make sure. Alright, and so to fill it out, what I like to do is I like to look at WX as a pair, and then I look at YZ as a pair. That way I can easily identify which one of these two, which column I'm looking at, and then which row I'm looking at. So let's go ahead and do that. So we see here that we have a 0, 0 and then a 0, 1. So we look for 0, 0 and 0, 1 right there, and we put a 1 where it belongs. And let's erase this circle. And then we move along here. We see another 1 right there. So that says 0, 1, 0, 0. So right there. Move along. We have 1, 0, 1, 1. So that's right here. And then we have 1, 1, 0, 1. So that's right there. So now we can make our circles. So obviously we can't make any pairs here actually. So we have to circle them all at once. Or by themselves rather. And then we can now make our equations. So actually all of these are going to have 4 letters in them because they're individual ones. So let's just write that out. So let's look at the first one. It's going to be this circle here. So that says W is 0, X is 0, so Y is 0, and then Z is 1. And then we look at the next circle. We see that W is a 0. We see that X is a 1, and then we see that Y and Z are 0, 0s. So that's not. Let me move this a little bit to the side here. And then we have WX as 1, 1, and then we have YZ, where Y is a 0, so put that there. And last but not least, WX, YZ, we have a 0 and then a 1, 1. So that's the equation for the A of the driver. So we're going to be moving on to B now. So we are looking at this column. And okay, so I'm going to be calling out whatever number happens to have a 1. So for instance, we're going to have a 5. We see that the 5 has a 1 here, right there, the 5. And then we're going to be looking for that cell in our kernel map. So let's go ahead and do it. So we have a 1 on the 5, so that's represented as 0, 1, 0, 1. So we put a 1 where it belongs. We have a 1 at the 6 position, so that's 0, 1, 1, 0. 0, 1, 1, 0, that's right here. Okay, and then we have a 1 at the B all the way down here, so that's 1, 0, 1, 1, so that's 1, 0, and then 1, 1 right there. And then another one at 1, 1, 0, 0, so 1, 1, 0, 0, so that's right there. And then we have 2 more at E, which is 1, 1, 1, 0, so right here. And last but not least, we have another 1 at the very last number, which is 15 on the F, so that's 1, 1, and 1, 1 right there. So that's where we place our 1. And then we're going to make our circles. So we start with this one. And so the individual circles happen to have 4 variables in them. So this if it's an individual one, it has to be, you have to specify which state is all of the 4 variables, all 4 being X, Y, Z. So let's just go ahead and write it out, the first one, while we're here. So WX is 1, 1 and YZ is 0, 0. So that's what that looks like. Like, I might run out of space here, so let's go this way. And then we can, do the other circles. So for this one, we can circle like this, but then we would have to circle like this one. So that just makes that's a waste. So we can't do that because we're going to have more logic gates. So what we do is we simply make these circles, and then that's it. We're done with our circles. So that's a total of 4 parts for the expression. So let's go ahead and write out the equation. So this is the first one I wrote right here. The second one is going to be here. So it's going to be x, y, z. And then this is a 0. And then we have a 0 on y. And then we're going to be looking at this circle here. This is circle number 3. And that's just simply w, y, z. And so let's explain why it's only 3 variables for this one. It's because if you look at x here, it's both on and off. So it could be either one. Therefore, the minimum expression for this is just going to be the w, which is 1 for both cases, and then the yz, which is 1 for both cases. Or 1, 1 for both cases. So that's how we choose our expressions. So what you want to look at basically is the variable that stays the same, whether it's a 0 or a 1. So now we move on to the last circle, and then we know that it's going to be three expressions only, or 3 variables. I mean. So that's going to be x, y, and z. And x is 1, y is 1, and then z is 0. So it's going to be a 0 right there. Okay, so now we look at c. So that's going to be this row right here. Now let's fill it out. So we have a 1 at 2. So that's 0, 0, 1, 0. So right there. A 1 at c. So that's 1, 1, 0, 0. Right there. 1 at e. 1, 1, 1, 0. Right there. And then f. It's 1, 1, 1, 1. Right there. Just like that. So let's make a circle. So that's one circle. And let's not forget this is going to be for c. So let's write it out. So we have 2 1s in this circle. So that's going to be wx. Wx is 1, 1 for both cases. And then we have we see that the y changes from 0 to 1 or 1 to 0. So that means that y is a changing variable, so y can be either 1. But if I look at z, it's always 0 for both cases. So I have to do z naught like that. Let's make my other circle. I choose this one. So we add. So that's once again wz, or wx I mean. And then we have a 1 for both cases on the y. So that's simply going to be y, because x is the one that changes, so that's the one we don't look at. And then we have a individual 1 here, and there's no other way of doing this, so we have to do all 4 expressions for this little one here, wx, y, z. So that's going to be like that. Okay, so now we do D. Let's go ahead and highlight D. It's going to be this one here. So we'll look at the first two. This is going to we see that we have a 1 on the 1. So there's the 1 is 0, 0, 0, 1. So right there. You have another one at 4, which is 0, 1, 0, 0. Right there. Another one at 7, which is 0, 1, 1, 1. So right there. And then another one at 1, 0, 0, 1. So it's going to be 1 0 0 1 here, and then another one at 1 0 1 0 right there, and then another one at 1 1 1 1. Okay. So now we have to make our circles. Let's go ahead and do them. So let's start with this one up here. This one, and then I'm going to write the expression for that. That's simply y naught. And so that's w naught, y naught, z naught. Second circle will be this one. So it's going to do a plus w. Well, actually w is the variable that changes between these two, so then we're going to start with x, y, z, and then we see that x is always 0 for both cases, so that's a 0. Y is 0 for both cases, and z is 1. So that's how that is. We do the other circle. Let's do this one here, and we write out all 4. So this is going to be x naught, and then z naught. And then maybe I can fit the last one here. It's going to be plus this last circle. And so this is x, y, z, because the x is 1 for both cases, and then the y and the z is 1, 1. So it's simply x, y, z. So now here we're going to be doing letter E. So let's highlight it. And then let's write our letter. Okay, let's fill it out. So we have a 1 at the 1 marker, or the 1 position, so that's going to be right there. We have another one at 3, so it's 0 0 1 1, so it's right there. We have another one at 4. So, you know, again, I'm looking at this list here, and I'm looking whether there is a 1 here. So just to reiterate what it is that I'm doing here. So we have another one at 4, so that's represented as 0 1 0 0. So 0 1 0 0. So that's how I fill this out, you know, just to make sure that we're on the same page. And then I move on. I see that there's another one on 5, which is 0 1 0 1. So right there. There's another one at 7, which is 0 1 1 1. So there it is. We have another one at 9, which is 1 0 0 1. So that's going to be right here. And that is it. So let me see if I got that right. Yes, I did. So let's make some circles and some expressions. So first circle, this one here. So that is going to be wx, y, and then the w is a 0, the x is a 1, and the y is a 0 for both cases. Second circle, this one. So then we add, and we see that the w changes for both of the ones, so we don't consider that. So then we say x, y, z, and then we know that the x is a 0, and we know that the y is a 0. Okay, and then the last circle we can make is actually this entire box here. So that'll give us a reduced expression. So it's just going to be w naught and z. So this is where, you know, you start to save on your logic gates. When you fill out the Kernel maps and you do these circles, you get, you know, the minimum solution. Later on, we'll see a situation where we have our whole list of expressions and we can start grouping which ones are repeated. And I'm going to do that after I'm done with all of the letters. Okay, so now we move on to F. And let's go ahead and circle it and write out to fill out the kernel map. So that's 0, 0, 0, 1. Yep. 0, 0, 1, 0. There. 0, 0, 1, 1. Here. And then we have another one at 7, which is 0, 1, 1, 1. And the last one is going to be the one at D, so it's going to be this one. That's the last one. And that is 1, 1, 0, 1. So 1, 1, 0, 1. Like that. Okay, so this is F that we're doing. So let's start with this circle here, and then we write the expression for that. So Wx, yz, and then we see that the y is a 0, so that's a not for that. Second circle is going to be this one. So we add a w, y, z, where the w is a 0, so that's a not. Third circle, this one, we add it, so that's a wx, z, w is 0, x is 0, so x naught and w naught, and g is 1 for both cases. And then last circle, it's going to be this one. So similarly, we have wx, and then we have a y, so that's a y like that. Okay, so now we move on to G. We highlight the G column, and we fill out the K-map. So that's a 1 here, that's a 1 here, 0, 1, 1, 1, so that's a 1 here, and then the last one is 1, 1, 0, 0, so 1, 1, 0, 0. So let's do the circle. First circle, I'm going to say it's this one, so that's wx and y, it's all zeros. Second circle, this one, plus wx, yz, so the yz are the zeros for this one, so I'm going to go ahead and do that, not, so that's y naught z naught. And then last circle is just also for wx, y, z, and w is 0, and the rest is 1s. So that is all of the equations, and let's put them all together and see how many expressions are repeated. Okay, so here I have placed all of my equations, and we have them from the K-maps that I did previously. So here they are, all the K-maps. So it helps to have them all here in one spot. That way we can begin to look at similar expressions. So in fact, I'm going to be using some colors here and making some circles to identify pairs, because I'm going to be using 2 input logic gates. So I'm going to be looking at specific pairs, and I'll be checking how often they repeat throughout all of these equations. So let's go ahead and circle the first pair here, and then with red I can circle the second pair. So basically all I'm saying is, okay, let this light blue box equal to w naught x naught, and let the red box equal to w naught x, so on and so forth. So then the green box is going to be dedicated for wx, and we see that we have another type of combination, so that's wx naught, so I'm going to be using brown for that. And then I'm going to continue. I see that there's a repetition of wx for the first part of part B, so let's circle that like that, and then red, so on and so forth. We don't see any repetitions here. Let's keep going. If you look at C, here's another repetition, and here's the same repetition once again, and then we have w naught x naught, so that's just comes from here, right? Let's keep going. We have w naught x, so that's just a red circle here. We have wx naught, so that's actually a brown circle. Let me redraw that brown circle here. Brown box rather. We have w naught x, so that is just a red circle. We have wx, and that is a green circle on the f equation. We have w naught x naught, and that is a light blue box. And then it repeats actually, so then we make the same circle here. And then it repeats once again, so we make a circle here. And then we have wx, we just make another circle here. And then w naught x, and that's just red, the red box. So now we go back up to the original expression, and then we look at the other two terms. But this time we're gonna do, instead of a box, I'm just gonna underline it as a pair. So here we have y naught z, so that is the blue underline. And then if we go on, this is y naught z naught, so red underline. And then we see that y naught z repeats here, so we do it like that. And then we have a yz, so we haven't seen that one before, so we're going to be using green underline for this one. And then we move on to line B, we see y naught z naught right there. And basically you can already see all of the logic gates that we're going to be saving here. We only need one logic gate. If you look here, we only really need one logic gate that gives us wx, and look how often it gets repeated. Same for the other ones. So this is an important aspect of designing, is saving money in your design. Okay, so then we continue in line B. We have y naught z, so that's a blue underline. We have yz, that is a green underline. And then we have yz naught. That, we haven't seen that pair yet, so we're going to use brown. Like that. And then we keep going. We see that there's no pairs here, so we just skip through it. And then we see that yz naught repeats, so that's a brown underline. We see y naught z naught, and we remember that from the first equation, and we're going to use red, so we highlight that in red. We have y naught z, and that is the blue underline. We have yz naught, that is the brown underline. And then we have yz in the end, so that is going to be the green underline. Let's keep going. We have y naught z. Y naught z is going to be the blue underline. We have yz, so that's not a specific pair, so we'll have to make that one. We keep going. Y naught z once again, blue underline. We have yz, so yz is the green underline. We have y naught z naught, so that is the red underline. And then for the last expression, it's a yz, so that is a green underline. It's a green underline here. So we can look at this overall and actually make some more circles. So we see that we can make this other circle. Let's do it in pink here. We see that this circle here, this whole section repeats itself, and we see it repeated right here. So we make a pink circle over that. What else repeats itself? This one here. I'm going to highlight it in yellow, or circle it in yellow, is B, and it repeats over here down on G, on the G equation. So we're going to be reusing the set of logic gates to replicate this signal. And then there should be one more actually. So let's go ahead and use the dark blue here. And it's going to be this one. We see that this one repeats down here. Okay, so now we have a nice visual way of seeing how each of these expressions repeats itself and how we can reuse each of the logic gates. So before we get into it, let me quickly explain. So for instance, if I want to map out or design a logic, make a design using the logic gates, and let's say I want to implement X, Y, Z, and all I have to me is available 2 input AND gates. What I can do is I can just do this. So put one AND gate here. Let's say this is WX, and then another AND gate here, and then I can hook it up to another AND gate here. So let's say that this is A. So then in my output I'm going to get A. This is how I can implement XYZ using 2 input AND gates. So that's what we're going to be doing here. Okay, so now here we are in multisim. I am reusing the counter that I made previously. I made the hexadecimal up counter. It goes from 0 to F, and it counts in hexadecimal, so it goes from 0, 1, 2, 3, 4, 5, 6, 7, 8, 9, A, B, C, D, E, F. And I made it using some JK flip-flops. So if you want to see how you make this circuit here and make this display count in hex, you can look for that video. But this display has a decoder built into it. So what I'm doing in this video is I'm making my own decoder. So we can see here that the bits are coming in on these 4 lines here. So we have W comes in here because W is the most significant bit, and then the least significant bit, it's going to be this one. I'm calling it Z. So if we look at our expressions, in fact, have them here, we see that they require the inverted version of it. So we see that A requires W naught X naught Y naught Z. So that's each, the first 3 is inverted, and then the second and the last one is not inverted. So it's a good idea to invert all of them. So that's what I did here. And then I have some labels here. So on the left, you can almost consider this as a bus actually. On the left is the WXYZ, and on the right we have W naught X naught Y naught Z naught. So when I'm implementing this, I can grab whichever one I need, whether it's inverted or not. So let's go ahead and look at this first one here. So this is an entire circuit dedicated for one section of the display. This is, or you can consider it as one expression. This whole design is for one expression. So let's look at the first one. We see that we need W naught X naught, and that goes into this top logic gate here. We see that we have Y naught and Z. So I'm grabbing this third one here, and then I'm grabbing the Z from here on the left, and I'm inputting it into the second logic gate. But these are multiplying each other, so then they need to go into a third AND gate. So that's where this one comes into play. And then eventually it goes into an OR gate, and it's combined with the rest of the expressions. So just one thing I'd like to point out on this first expression, we see that Y naught Z is repeated. So all I need is one logic gate for this expression, y naught z. So that's in fact what I did here. So y naught z is this specific logic gate here. We see that we have y naught coming in here, right? Let's have it labeled, and then z from the other side. And then I am reusing it to go into this third portion of the expression right here. So in fact, I don't need this one. Typically, if you were doing this very rigidly, you would hook this one up like this, call it that is y naught z. But the reality is that we don't need it, so we save money on using the least amount of logic gates. So we delete that. And we see that here's the output of that. And it is added with the AND gate. No, not added, multiplied with WX. So let's look at this one that's coming into it. It's supposed to be WX, and so we see that it is. So it's W, that's the first one, and then the second one is X. And then eventually, the last expression is going to be WX naught YZ. So let's look at this one. So that's W, and then we have X naught. We see that from this expression. What else is it? Y and Z, and here it is. So here's Y, and then here's Z. And I already have the whole circuit wired up, but you can see basically this sort of bus of wires. This is all of the logic gates that we are reusing. So this is very good for us because we use the minimum amount of logic gates. I believe this particular setup uses only about 48 logic gates. So it's pretty good. And so I guess let's take a look at the rest of it. And that is the last one. We see that the last one uses 2 OR gates, 2 AND gates. So by the end of it, pretty much everything has been already made beforehand. So we are reusing it. We are reusing a lot of what's been already made. So in fact, if we look back here, this specific decoder actually contains logic that is similar to what you see here. I don't know exactly what it is, but what I have here performs the same task as that, because this automatically converts the binary bit into the binary number into a hexadecimal representation. So that's what I'm doing here. So let's go ahead and run it and see what we get. I'm going to be running these two together, and what we should see is that this decoder or this display should have the same as this one here on the right. So on the right is going to be the output of my own decoder. So let's see if it works. Starts at F, 0, 1, 2, 3, 4, 5, 6, 7, 8, 9, A, B, C, D, E, F. And there it is. Let me see if I can look at it from an overall perspective. It gets quite small here. Kind of hard to see. So there it is. So this is what the whole design looks like. It's fairly complex. On the left is my counter, just using the JK flip-flops, and on the right is all of this is what I designed. This is considered the decoder of a binary counter, or a binary number rather. So if you're looking to implement this, often in YouTube you see people that they don't really show you the process, they just show you the circuit. But if you want to implement yourself, you have to get to these equations. Now, I already showed you how to get to these equations. And what you can do is you can sort of get a piece of paper and write out. You can sort of draw the schematics of how this would look like on your own. And when you're done with it, you should end up with something that looks similar to this. If you're reusing the appropriate expression, like if you're reusing each of these pairs, like how I have them highlighted, you'll end up with a design where the first one reuses just once, and then in the last one there's a lot more reuse going on for this last one. So that's why as you go down on this circuit, it gets more and more simpler, because you're reusing a lot more and you need less logic gates. So it's important to make sure you know how to get to these equations first before you go into the design process. So that is all I have to say about this. If you have any questions or comments, please leave them down below. And thanks for watching.